I'm Robert Yenokyan, head of AI at Pinsight. And this workshop is going to be about training unbiased and accurate AI models. What is a fair model? Like, what is fairness in machine learning? Let's first of all consider that. So it's basically we need to construct an optimal machine learning model subject to some fairness constraints. So that's basically a constraint optimization problem. So there are sensitive and features and legally protected features. This could be age, gender, race, and others depending on use cases. The idea is that our and give different results based on those sensitive features. And the main reasons that machine learning models are unfair is because the training data is biased. There's a lot of bias in the training data, and uh, biased data just will give us a biased representation. Um, the training data is not representative of the actual data that we're going to predict on. This is also the case when over the time data changes and it's becoming less and less representative. And when training the machine learning model, we choose not the right objective function to optimize. So let's go over some fairness definitions. Because this is machine learning, we need to quantify those whether the model is fair or not. So there are a couple of definitions that are like widely used. We'll consider three of them, but of course there can be some custom definitions depending on use cases. So the first one is equal opportunity. Um, this requires equal true positive rates across sensitive subgroups. So let's first of all see what true positive rate is, then we'll come back to this definition. So here we have the confusion matrix. What this is the matrix of predicted and actual values. Uh, if we predict a value as positive class and it's actually the positive, then it's called true positive. When we predict it as positive, but it is negative, so we have an error. So we didn't predict it correctly. So that's called false positive. When we predict it as negative and it is positive, it's called false negative. And when it's negative and we predict it as negative, then it's true negative. True positive rate is, here we can see, is true positive divided by true positive plus false negative. So it's true positive divided by all the actual positive observations. This basically means from all of the positive observations, how much in percentage form, how much we predicted correctly. This number ranges from 0 to 1, 0 if we didn't predict any, and 1 if we predicted all of them correctly. So now we know what true positive rate is, and it says that it needs equal true positive rates across sensitive subgroups. Mathematically, it's this equation, probability that our prediction belongs to the positive class, given that it's actually in the positive class and it's in the subgroup A, is equal to the probability that it's or that we predicted as positive class. It's positive given that it is actually positive class and it is in the sensitive subgroup B. For example, if we have our sensitive feature is gender and it is binary encoded, male, female, for example, then it says that in each of those subgroups, the true positive rates should be equal. The next one is equalized odds. So this one requires equal true positive and false negative rates across sensitive subgroups. So in this case, we have two constraints. So it needs to have both true positive and false negative rates. So it's basically equal odds plus another condition. Let's see what false positive rate is. So false positive rate is false positives divided by false positives plus true negatives. And this is out of all the, it shows out of all the negative values, how many we predicted incorrectly. Because false positive divided by all of the number of negative observations. And mathematically, it's this equation. And then the third widely used definition is statistical parity or acceptance rate. So this one requires that observations in sensitive groups have equal probability of being assigned to predicted positive class. So basically, the probability that again, let's get the example of gender, male and female. So for males, the probability that we will give it a positive class should be equal to the probability of giving positive class if it were female. So basically, these are the three mainly used fairness definitions. Okay, so there are we can see if the model is fair or not by calculating those values, and there are a couple of ways to do bias mitigation. That is to train or to get the model to not be biased. So the first one is pre-processing. These methods basically modify the data representation in a way to learn the data representation along with using over or undersampling the observations in sensitive groups. The second one is during processing. Those are special algorithms that try to optimize both the accuracy and the fairness metric, but they are model specific. Post-processing, so when we have already a trained machine learning model and we want to, we cannot retrain that model, we just want to make the predictions more fair, we do this post-processing, which is basically adjusting the decision threshold. So classification models gives us the probability of that observation being class 0 or class 1. And then we need to decide a threshold to map it into positive or negative classes. There's some special algorithms or so-called meta algorithms that at the end we have like probabilistic models and the results are the predictions are probabilistic. So if we run it a couple of times, it will give different results. So let's just compare all those models. And of course, we have the other one, the genetic optimization, which we'll cover later. So during processing, post-processing, special or meta algorithm, and genetic optimization. The pre-processing, okay, so let's go by the types. So model agnostic. This means that it can be applied to any type of model. The during processing doesn't have this because They construct special algorithms just to train models, so it cannot be used for all the type of models. The pre-processing and during processing methods, they cannot have like any fairness definitions. There are special definitions used to do these processings. Can they support multiple sensitive features? The pre-processing approach cannot do that, and the post-processing approach again cannot do that. The rest are able to handle. No need for sensitive feature time. So it's important. Let's say it's a bank and it wants to predict whether the person will go default on their credit or not. So whether they should give that person loan or not. And the post-processing model just takes different thresholds for different subgroups. So again, if we have this sensitive feature of gender, and we have male and female, we will have different thresholds for those two groups. Let's say it's 0.3 and 0.4 for each of them, and the probability that our model gave is 0.35. So basically in between these two. If it is the first group, then we will predict as 1 and give it that they will default. And it is in the subgroup 2, then because the threshold is 0.4, then we will say that they don't default. And if we don't have this feature at the time of the prediction, we cannot make that adjustment. And there are legal and regulatory issues with using the sensitive features at prediction time. And non-probabilistic models, all of them are good except for this meta algorithm. And why is that bad? Again, in the bank example case, if we run the model, if we try to predict on the same person multiple times, it will give different results each time. So one time it will say that the person will default, the other one that they won't default. So that's a problem for us. Yeah, and the genetic algorithms, which are trying to optimize the model, do hyper models that have all those don't have any of those problems. So they are model agnostic. They can handle any fairness definition. They can handle multiple sensitive features. There is no need for the sensitive feature at prediction time, only at the training time. And they don't give us probabilistic models. So let's see what are genetic algorithms. Genetic algorithms are a type of general class of optimization algorithms inspired by natural selection. We start with a population of individuals. So each individual is a solution to our optimization problem. And each individual has some features or so-called chromosomes. So are done on each individual to move the whole population to the optimal solution. These operations are crossover, mutation, selection. We'll go over each of them and see what they are. So the first one is crossover. It is used to generate new offsprings by combining genetic information from the parents. So usually we have more than 60% of the population getting crossover. It ensures the survival of the fittest. So it ensures that the solutions, the best solutions to our optimization problems will survive and will go to the next generation. So it is passing the genes of those strong individuals. There are a couple of ways we can do a crossover. The simplest way is we take a crossover point, so a random point, and we swap the sequences up till that point. Here in this example, up to the crossover point, we swapped the gene information, so the blue and red swapped places. And the children, the two individuals that we get, will be considered for the next generation. There are a couple of more ways to do crossover. So we can select two crossover points and swap the information between these 2 points. Then we can do individual chromosome crossovers. So with some probability, each individual chromosome is switched. So in this case, we don't switch sequential parts, but it can be any of the chromosomes. These are basically the 3 types. And you have to try and experiment to see which one works best for each case. The second one is mutation. So the mutation, it randomly changes the value of the chromosome. We usually try to do mutation on a very small percentage of individuals. It tries to add diversity to the population, so it's not saturated. In this example, we have our individual where each chromosome is binary, 0 or 1. And it randomly flips the value of one of the chromosomes. So in this example, in this 1 was flipped to 0. When we have real values, instead of binary values, then we can do Gaussian mutation, which would add a Gaussian random variable to that value to randomly change it to something else. The idea of the mutation is that when the population, our solutions are stuck in a local optima, it wants to change some features, so it will get out of that local optima and find a better one. The next one is selection. So the selection is the process of selecting the individuals for the next population. There are a lot of algorithms for selection. The 2 main ones are tournament and roulette wheel. So how does tournament work? We select, let's say our population is 100 individuals. We select 3 randomly and then compare those 3 and take the best individual. So the best solution out of these 3. We will repeat this process 100 times until we get a population equal to 100 individuals, and then that will be the next generation. And roulette wheel approach, in which the probability of choosing an individual is proportionate to its fitness value. The fitness value is basically how good of a solution that individual is to our optimization. Okay, and there's the Hall of Fame, which are top-end individuals that are guaranteed to pass to the next generation. Why do we do this? It's possible to lose the best solution from one population to the next. And mainly it will be because of mutation. So if the mutation changes something in the top individual, it becomes a bad solution, then we will lose that. We can lose the top individual also. And it's possible we will lose the individual because it just for the next population. And depending on like tournament and roulette wheel selection processes, it's possible to lose top individuals, but there are some selection algorithms that take, for example, uh, the top percentages of only the top best individual. In those cases, we will not lose them. Okay, so the fitness value. It's a score that tells us how strong that individual is. So how good of a solution that individual is to our problem. For different problems, fitness values will be different, and it is crucial to select appropriate fitness values. The optimization, so we want to optimize for that fitness value to optimize for our problem. Okay, so let's say we're trying to optimize the model. It's a classification model. We want to optimize for statistical parity, and not only to make the statistical, not only to make the model fair, but also we want to make the model accurate. So we would also want to optimize for ROC or some accuracy metric. So we can consider the difference of statistical parity between those two subgroups. We will take the absolute value of this difference, and we will give it. It would be our delta. So basically, we would try to minimize this difference, delta, and minimize 1 minus ROC. So ROC is a number between 0 and 1, and it tells us how good of a model it is. The higher the value, the better the model. So if we want to maximize ROC, we can minimize 1 minus ROC. This is basically the same thing. And if we try to do this, try to minimize the difference and minimize 1 minus ROC, we would have two, we will try to optimize for these two fitness values, and it will search all the Pareto curve. So let's understand what a Pareto curve is. Okay, in this case, we want to optimize for two functions, f1 and f2, and the lower the value, the better it is. So in this case, we wanted to minimize the difference, delta, and minimize 1 minus ROC. Let's take one of the white circles, and let's compare it to, let's say, this one. The second point has a low for f2 and a lower value of f1. So it is better than the first point because it has lower value for all of our metrics. So we say that the second point dominates the first one. And the Pareto optimal solution is the set of all those non-dominated points. So all the blue ones are non-dominated points. This means that we cannot find another point that has better values for all of functions. Let's consider this dot and the first and the second blue dots. So the first one, it has a higher value for function 2, but a lower value for function 1. So basically, we cannot compare those two. There is a trade-off between these two. And when we try to minimize the difference in statistical parity and minimize 1 minus ROC, What will happen is we will get this kind of set of best models, non-dominated clients, um, and this will be our best models. Then there's a trade-off. So we need to decide how much accuracy are we willing to lose to gain some points in fairness. But this has a couple of problems because it tries to search for all of the Pareto curve, and the optimization process will be very resource consuming. Instead, we can focus our search on some specific part of the Pareto curve. What do I mean by that? Um, so we can define our model fair if the difference of statistical parity is less than or equal to some epsilon, where epsilon is a predefined threshold. So there are some regulations that state that this difference shouldn't be more than some number, let's say 0.02, 0.05. And if it is a number, then the model isn't fair. In this case, we want to consider only the models that meet this condition, that is less than this epsilon, and it will just search a subset of the Pareto curve. So let's say our function one is the function for the difference, and function two is 1 minus ROC. So it will just try to optimize to find the best model in just some area of this function. So it won't go over all of the points, but it will like search a part of the curve. How can we do this? So we won't do we can do multi-objective optimization. In the first case, we try to minimize the difference and minimize 1 minus ROC. In this case, we can try to create a binary variable. So if the difference is less than epsilon, we will get it 0, otherwise 1, and we will try to minimize this. So it will just be 2 values. Or another better approach would be to multiply ROC by this binary variable. So if the model is fair, then we will get the result will be 1, and if it isn't fair, the result will be 0. And we will multiply that by our accuracy metric, in this case ROC. So if the model is not fair, then that will be 0 times ROC, which will be 0. And if it is fair, then it will be 1 times ROC, which is equal to ROC. So we will try to maximize that value. In case it's not fair, it will be just 0. And if it's fair, then we will find the set of the models that are fair, and we will take the best one from that. There are a lot of definitions for the for our fitness value, and that's depending on your use case, what you want to accomplish, you can change the fitness value. So if we want to find all of the models, all of the set of the models that specify these conditions, we will just minimize the difference and minimize 1 minus ROC. If we want to look only at the specific part of the Pareto curve, we would just do this ROC times 1 if it is fair, and ROC times 0 if it is not fair. So and you can be creative and define your own fitness value. Now I will show a visualization of how this genetic algorithm work. Let me, so in this example, we're going to have 200 individuals in population. Each individual will have 100 chromosomes. Each chromosome is a binary variable, so it's either 1 or 0. And the objective is to maximize the sum. So all chromosomes should equal to 1. This is obviously like a very simple task, but it is very good for understanding how it works, how each of the operations, crossover, mutation, and selection work. And it's great for visualization. So our parameters will be 1% probability of mutating and 70% probability of crossover. Our selection algorithm will be tournament selection, where we will randomly select 3 individuals and take the best one from that. Okay. So this is it. Basically, we have 200 rows and 100 columns. Each row is one individual, and we want the values are 1 or 0, yellows are 1, and so our objective is to have a solution where all the observations are ones, so it's all yellow. So here we have like a random population, and we try this genetic algorithm. So already at generation 11, we see that a lot of the values are yellow, so it's learning, but there are some places where almost all of the chromosomes are blue, and it needs to learn that those values should become 1 instead of 0. So we see that it's improving. So the rate of the improvement isn't that great because like at first it learned very fast, but now the learning, so the improvement isn't, the rate is getting lower and lower. So basically at Gen 37, we found solutions. All of the population is the same, where only 4 chromosomes remain zeros. And no matter how many times we do crossover operation, the value of the 0 won't change to 1 because we're just swapping the values. So we're swapping the chromosomes of individuals in this population, and none of the individuals have a value of 1 in that chromosome. So no matter how many times we do crossover, we won't change the value. That's where comes the mutation. So if the value of this one of the 4 chromosomes is mutated to 1, then the result will improve, and it will quickly learn that all of those in all of the population should be 1. So from generation 37, it's this, and let's see what happens. Okay, So from generation 37 to generation 52, we didn't have any improvement. It took us 15 generations to find to be able to mutate this chromosome and find a good solution. And let's see, so just 5-6 generations later, we have we learned that this chromosome should be 1 instead of 0. And then we're again waiting. Those blue ones that you see changing, it's because of, so it randomly tries to mutate those values, but because it changes from 1 to 0, the fitness value becomes worse and it gets to the top. So it's those individuals are sorted by their fitness value from bad to good. So at the bottom, we have the good ones. Again, still no improvement. We have to be lucky. So we found that this value should also be 1. So because the mutation probability is only 1%, then in this population of 200 people, only on average 2 people will be mutated. The next one, and okay, so at generation 92, 93, we find the best solution. So it will run up to generation 99, and this is the result. It's all yellow. So on average, the population, the fitness value of the population improves. And this just shows, like this part shows the importance of the mutation operation. No matter like how good of a solution we get, we might be stuck in a local optima. The all of the population is saturated. All of the observations are, all of the individuals are the same. They have the same chromosomes, and we're stuck in the local optima. So we need this mutation operation to just to try to explore other areas and maybe find a better optima. In this case, we just it's a simple case, and we find like the best solution. But in a lot of problems, there you don't know what the best solution is. So if you're trying to optimize, to do hyperparameter optimization for your machine learning model, where you want to optimize accuracy, then you won't know what is the maximum value that it's possible to get. Like it's 100, yeah, 100 accuracy, but maybe it's just not possible to get there. Okay, so hopefully that got like you have this intuition of how it works. Okay, so what can be done in machine learning with genetic algorithms? We can do feature selection. So if we have a model and a fixed set of hyperparameters, we can try to find the best features, the features to use in the model. We can do parametric model training. For example, logistic regression, where it uses a linear combination of inputs and then puts it in sigmoid. So in this case, we can try to learn the best. We can try to find the best weights for logistic regression with genetic algorithms, but it won't be efficient. So genetic algorithms are general class of optimization, so they can optimize any kind of um, that you can calculate, like a fitness value. But in cases where there are already specific algorithms defined for that problem, for example, neural network training or where it uses stochastic gradient optimization technique, or in logistic regression, all those kinds of trainings, a genetic optimization will take more resources, more time to get the same result techniques. But on the other hand, when there is no information on gradients, no, there is not like there isn't any special algorithm that has been created for that problem, then you can genetic algorithm. It can be used to do hyperparameter tuning. Uh, that's basically this approach to training accurate and fair machine learning models. We do hyperparameter tuning of a machine learning model where we try to optimize for accuracy and for fairness. And there is this neuroevolution tries to generate neural network parameters, topology, and rules. So what does this mean? In neural network, we have neurons, and each of the neurons have weights. So these are the parameters that it tries to optimize. That's similar to what I said about parametric model training, so for logistic regression. But it also can find the topology of neural network, so the architecture of the neural network it can learn, and the rules. So whether we need to do dropout, what the activation function we need to use. All of this can be done with neuroevolution. It's a resource heavy operation, and it's not as simple as just because the operations are the same, but they are adapted for neural networks. Because the individual size, the number of chromosomes in each individual is not fixed. Let's say we have a neural network with 100 neurons and another one with 120 neurons. So if we consider them as two individuals, the first one will have 100 chromosomes, the second one 120. So because we are evolving the topology, all those operations will be a little bit different. But the ideas are just the same. There is like another optimization technique, Bayesian optimization, which is also a general class of optimization technique. Again, it can be used in cases where there is no defined already optimization algorithm. We can use Bayesian optimization to do parametric model training, to do feature selection, to do hyperparameter tuning. I don't think it's possible. Maybe there hasn't been done research to do neuroevolution with Bayesian optimization. And it's my preference to use genetic algorithms in those cases. But they are basically almost the same. They will yield the same results in the long run. But some cases Bayesian optimization beats genetic, and the other cases it's the opposite. So you never know which would give you the best result in the shortest amount of time, or consuming the less resources, which would be not only time but also CPU, GPU power, etc. So I will go over Python code, just how we can do feature selection. Because feature selection is actually, we'll use chromosomes of binary values, and we saw the visualization, we considered the binary, it's the easiest version, let's say. But it can be adjusted to do hyperparameter tuning, just because in hyperparameter tuning we have real values. For example, if we try to learn to optimize the parameter of a tree-based model, there is, let's say, and it is, for example, an integer value from 3 to 12. Then the crossover and mutation are a little bit different, but the coding part will be a little bit longer. That's why we're just gonna go over this feature selection part only. So we are importing random, NumPy, and pandas. Random and NumPy for the genetic algorithms, pandas to read our data frame. The library DEAP is the main library used for this genetic optimization. We import LightGBM classifier because we want to train a network, a machine learning model. And then we import model cross-validation score because we want to do cross-validation and optimize for ROC-AUC. Okay, so the first thing is to define our fitness value. This will be the function eval model, where the input is the individual. The individual should be binary, 0 and 1s, where the length of the individual will be how many columns we have. And if a specific index, so let's say the first chromosome is 1, that means that the first column is included in the model. If it is 0, that means it's not included. So we will take all of the columns where the where the chromosome of the same index is equal to 1. Then we'll create a LightGBM classifier with the predefined best parameters. And then we will do cross-validation with that model, taking only the columns. We'll do tenfold cross-validation, and we will be optimizing ROC-AUC. So it will give us 10. It will give us 10 a list of 10 ROC-AUC scores. We will just take their mean, and that will be our fitness value. So we will be optimizing the average of the ROC-AUC in a tenfold cross-validation. Again, here the model, it could be anything. It doesn't have to be LightGBM classifier. It could be any type of model, and the data, it could be anything. It needs like X0 is your data, training data, and Y0 are the labels. Here it gets a little bit tricky. Not so tricky, but this is the syntax for creating individuals, population, and all the operations. So we do fitness marks. Just this is the name of the fitness value. We say weights is equal to 0. This means that we're trying to optimize for only one objective, and we're trying to maximize it, because if it were -1, then we would try to minimize it. we would create an individual, which would be a list, and it will have this fitness value that we will try to mark. Then we will register each of these attributes. We name it attr boolean, and it will be a random number between random integer 0 or 1. So it's boolean. That's why random integer. Then we will register each individual. We will say it's we're repeating this. It's in the list. Its values are attr boolean that we created in the above line, and we say it has as many chromosomes as our data has columns. So if our data has 10 columns or 10 features, then our individual will have that length. The length will be 10. We create the population, which is a list of individuals, and the individual is this one that we created. Our evaluation is how we should evaluate the fitness score. It is the eval model, the function that we just created. We are specifying the mating or crossover. In this case, we are taking 2-point crossover. This means that we will randomly select 2 points and swap the gene information between these 2 points. We will do a mutation on each individual chromosome with a probability of 0.05. So for each individual, it will go over every chromosome, and with 0.05 probability, it will flip the value to, so it's Boolean, binary, 0, 1, it will flip to the other one. And our selection is going to be tournament selection with tournament size 3. So we will select 3 individuals each time, and we will take the best individual from that. So this we're just setting up all of it. We will create a population of 300 individuals. Here we calculate the fitness values. So we use toolbox.evaluate, which if we go here, it's the this function. And we will map it over all of our population. We will assign their fitness values, and we will assign 3 more variables. So the first one is the crossover probability, 0.5. So with 0.5 probability, we'll do crossover operation on 2 individuals. And the mutation probability, which is 0.2 or 20%. With 20% probability, we will select an individual to do mutation. This means that 20% of our population will get mutated. And here, each chromosome in those selected individuals will have 0.05 or 5% probability of being mutated. So in this case, the mutation probability is quite high in both the number of individuals that we try to mutate and the number of chromosomes. So and g is equal to 0. This is just to track our generation. We'll start with g is equal to 0, so the first 0 generation. We specify a number of generations, so how many generations we want to do the optimization. G plus equal 1, so we want to our counter. We select as many individuals from our population as we have population. So we want to have the number of individuals in a population fixed. It will use the selection method that we defined earlier. We will copy all those individuals, make a copy, just not to, it's because of the library and Python. This is the way to do it. And here we will do the crossover. What we do is we take all the even and odd individuals, and we see if it is we'll generate a random number between 0 and 1, and if this number is less than our crossover probability, which we defined 0.5. So in half of the cases, we will do crossover with them, and we will delete their fitness values. Why we delete them? Because individuals, and we need to calculate the fitness values for them. Then when we do the crossover, we loop over each offspring, so each of the individuals. And again, we generate a random uniform variable between 0 and 1. And we say if it is less than our mutation probability, which in this case 0.2, then we will do a mutation operation on that individual and delete its fitness value if it has some. We will find all the individuals that do not have fitness values. So all the individuals that got crossover or mutation, and we will calculate their fitness values. Because we are doing a timefold cross-validation, this fitness value is very time-consuming, so we want to be as optimal as possible. And for all these individuals, we will assign their fitness values, and then we will update our population with the new offsprings. And this is basically it. It's just a couple of lines of Python code, and we can do any kind of optimization with this. We can do with this code, you can do feature selection for a given model with given set of hyperparameters. And for trying to do like hyperparameter tuning with multi-objective optimization, there needs to be done a little bit more work in defining the fitness value and creating this part. So you need to be a little bit familiar with the library in order to be able to create each of the individuals. So in this case, our individuals had only binary values. It was a random integer between 0 and 1, but let's say we're trying to do hyperparameter optimization. Some of the variables need to be real valued. Some of them are integers between a range. For example, maximum depth would be from 3 to, let's say, 12. So it's a little bit more work, but the same ideas apply. And it's we do some imports, and it's less than 50 lines of code, and you can do any type of optimization with this. The library that I use is DEAP, Distributed Evolutionary Algorithm in Python. They have very good documentation. I think it's the best library for doing evolutionary algorithms. It doesn't support neuroevolution, but for the rest, it's very good. So you can connect me on LinkedIn. This is the QR code for my LinkedIn profile. I will be posting a series of blogs about genetic algorithms, how to do them, in NumPy, then using this library, and then doing all of this like hyperparameter tuning, feature selection, all of this in Python. It's just it will be a couple of blog posts, and it will take some time to read through all that. So you can connect me and follow me for the updates. Thank you very much. I think we're out of time, right? So yeah, this will all. Thanks again.